This section will really be focused on the log rules, but before we get into those rules, just want to kind of redirect you to a couple of key things here. So this would be one of those question and response from y'all kind of deals. So log is an answer to the exponent. That's fun to play ping pong off of there. So a log is an exponent, and if you remember that a logarithm is always an exponent, it's going to really make all these rules fall into place. Now, something I did with the very first problem of the week, and I don't know if I explained it as well as I would have liked to, so I'm going to do it one more time, make sure it kind of makes sense. Again, keeping in mind that a logarithm is an exponent. It will follow all the exponent rules you're familiar with. So I gave this chart to you back at the first problem of the week, and it was kind of the order that you've learned math. First thing you learned was add and subtract and so on. And what you get here, it's just kind of an organized way to show the different functions of math. It's multiplication is a fast way to add. Powers are a fast way to multiply. Same thing on this side. These are all the opposites of the first part. So basically addition is the only math there really is. You can boil everything down to addition, and I think I mentioned this before, that's how computers work. But anyway, let me just run through how to use this chart. So let me give you a few scenarios. Let's say you've got 2x squared plus 5x squared. So the way you use the chart, the big numbers do what it says to do. It says add, so they're going to add. The little numbers, and I'm using Fleshman coined this, so I'll give him credit. The little numbers, they're like the children. They do something. They got to have something a little bit easier. So if the big guys, the adults are adding, the little guys, they can't quite do that yet. So they're going to do something simpler. They're going to go down one level on the chart. So they do nothing on this case. So that's always the way the chart works. If it's a plus sign here, the big numbers are going to add. The little numbers do one thing below, which is nothing, so they stay the same. All right. The next piece, you got this term times this term, so the big numbers are going to get multiplied because that's times, which means the little numbers are going to do something easier, and they're going to add. That's x to the first technically, so x cubed. And then finally, I've got a number raised to an exponent. So 2x cubed squared, well, the 2 is going to get squared, but then the little numbers are going to do something a little bit easier. They're going to multiply. So 3 times 2 be 4x to the 6th. Anyway, that's how you use that chart. So the key thing is when you add two terms, you do nothing to the exponents. When you multiply two terms, you add the exponents. When you raise an exponent to a power, the exponents get multiplied. So here's the heart of the section, and then we'll do a few examples with this, but I do want to run through a few proofs with you to make sure these laws make sense and why they do exist like they do. So we've got the product property, the quotient property, and the power property, I believe is what it's called. So the first one, product property, says if you take log base something of two things multiplied together, it can be written out as the log of each one separate but added together. So let's prove why that has to be true. And to prove things, we're always going to start with one side, and we're going to see how we can turn it into something else. So over here, and some of these little sides I pull up, it's if you ever get to proof level thinking, like college level proofs, there's a lot of sitting down, trying things, balling up paper, starting over. And it's just, here's the thing that somebody tried that worked. That's really all this comes down to. I wouldn't expect y'all to come up with what's underneath this little cover here. So I just call it a side. But I'm going to let log base A of u be n. And I'm going to let log base A of v be n. I'm just kind of making these two true statements, if you will. And then they can be rewritten where a to the n is u, and a to the n is v. So those are just, I made those up, but I made them up in a way that's actually going to make this really helpful and make it really useful. So if that's the case, then, so if those are true, then log base A of u is a sub n. I can sub in a sub n for u, and I can sub in a sub m for v from what I came up with over there, or what I made up. Now, if you think about kind of how this piece right here is going to go, So let me kind of get the log part started. Well, these are both a times each other, and the powers, since these are going to be multiplied, the powers are going to add. So n plus m. And then you did learn that rule in the last lesson where if you have base a of a, they basically cancel out. So that becomes m plus n. And from the two definitions I came up with in the beginning, I know I made those up, but they were true, and by plugging them through all this, it worked out. So n is log base a of u, and m is log base a of v. So there you go. That proves that if you start here, that must be true. Quotient property is really similar. It's really almost the exact same proof. So I'm going to refer you back up the screen if you get confused on what I'm doing here. But I'm going to use that same aside. So u, we said, was a to the n, and v was a to the m. So let's put that in here. And since both of these are a, and they have exponents, those exponents will get subtracted. So that would be the same thing as n minus n that way. And log base a of a cancels out, so that's left with just n minus n. And if you go back up and look, n was log base a of u, and m was log base a of v. So that's got to be true as well. For the power property, I'm going to do a sort of proof, which I think just intuitively makes a lot of sense. But I'll do the actual proof also, just to make sure that you get to see that. So what it says, if I have log base a of something to the x power, that x power can be moved out front and be multiplied by the logarithm. So here's not really a proof, but I think it gets the point across. Let's think about what an exponent is. So if that's what I've got, we could say it's the same thing as log base a of b times b times b times b, however many times you've got here, x times. Because that's what an exponent is. It just says multiply b by itself over and over and over this many times. And this kind of goes back to the chart. Here's what a power is in multiplication. Let's take it back one more step. What does it look like in addition? So if you kind of break it up even more, and this is by using that product rule, well, we've got log base a of a bunch of b's multiplied together, so that could be log base a of b plus another log base a of b plus another one, and we do that x times. And hopefully that kind of is enough just intuitively to think about it. If I have log base a of b added together x number of times, well, it's kind of like this. If I had 2 plus 2 plus 2 plus 2 plus 2, it'd be a lot faster to just say, all right, well, that's 2 times 5, and be done with it. So I could say that's log base a of b times x, however many times. And so that's an intuitive way, I think, to get to this rule. Because again, it's coming from exponent rules. A logarithm is an exponent, so it just comes back to those exponent rules. Here's the actual proof, if you want to see that part. So the same thing we just talked about. With a proof, we want to start with one side and turn it into the other. So I've got another little aside here. Again, I wouldn't expect you to come up with this. Just somebody sat down and played with enough things that this was the one that won. This worked out. So let b equal a to the n power. Okay, so let's see how that plays out if you plug that in. So log base a, we're going to say b is a to the n, and it'll be raised to the x power. So just a substitution, that's all I did. So you might be seeing this happening and thinking maybe I can cancel something out, and soon you will be able to. But before we take care of that, let's take care of these exponents. It's going to make the process way easier if we kind of hold off on this for now. So a to the n to the x, you've got an exponent raised to another exponent. So those are going to end up multiplying. And now you pretty much came down to that same scenario you had from the first two, where it's log base a of a. They can cancel out. You just have n times x. All right, well, it seems like we're kind of stuck, but if you look back at the aside here, if you redefine it, then we could say log base a of the result is equal to the exponent n So that means n is log base a of b. So log base a of b times x. I'm just putting that in there. And that could simply, through commutative property, be reversed and turn into this. So that's the actual formal proof of how that's going to work. So now let's actually use the rules. And you're probably going to get sick of me saying this all year, and you probably already are. But in calculus, these logarithm rules are going to give you ways to do things without a calculator. And it's probably just going through the practice, you're going to start to see a little bit of a feel for that. Some of these practice problems, you might not see any kind of definite connections down the road. And it might be scenarios that you think about like this and say, when would I ever do that? So just keep that in mind. This is just giving you something concrete to go on. Honestly, you're probably never going to do this specific example in real life ever, no matter what kind of career you get into. But the idea that this conveys will lead to some bigger things later on, especially in calculus. So keep that in mind if it feels kind of weird. So I'm giving you two things already done. Log base a of 2 is 0.45. Log base a of 6 is 0.65. And then I'm asking you to find log base a of 12. So really the thing to be thinking about, the skill that you're really trying to understand here, if we know that the product rule happens, we can multiply two things together and their logarithms add, or if we divide two things, their logarithms subtract, then look at what we've got. We've got a log base a of 2 and a log base a of 6. And if you think about 2 and 6 and how you can make 12, well, what they're asking you or wanting you to do here is to say, all right, well, log base a of 6, log base a of 6 times 2 would also be 12. And by the rules, log base a of 6 plus log base a of 2 would be the same thing as that. And then you plug in your numbers. 0.65 plus 0.45, we get 1.1. So it's just making you think about this by hand without using a calculator. That's really what they're trying to emphasize here. Okay. And this with the same givens, but this time find log base a of 3. The givens were 6 and 2, so log base a of 6 divided by 2, that would be 3. And by the quotient rule, log base a of 6 minus log base a of 2. Now this one you got to be careful because it is with division or with subtraction, order matters. And you're dividing 6 by 2, so it's got to be 6 minus 2 as far as how the logs are set up. All right. Log base a of 6 was 0.65 and the other one was 0.45. For a difference of 0.2. Now these next couple examples, these are really getting closer to what you're going to do in calculus. Let me just leave it at this. When you do your calculus magic, it's a lot easier sometimes if you expand these things out. You might start with something that's really going to be difficult to do your calculus with, but by the time you expand it out into several logarithms, you can pretty much do most of them in your head and be done. That's why this is important. So log base 2 of 72, we're supposed to expand this out. What I recommend first is take the number that you're trying to, is inside your logarithm and break it down to prime factors. So 72 is 8 times 9, 8's 3 2's, 9's 2 3's. Once you've got this into prime factors, just think about kind of how you'd write that. 3 2's would be 2 cubed, and 2 3's would be 3 squared. So 72 is the same thing as 2 cubed times 3 squared. So I'm going to take one step just to write that in my logarithm. And you may not need this step, but I just want to make sure it's pretty clear what I'm doing, especially if you're just trying to follow along. So first up, these are multiplied together, so I can split them up by the product rule. So log base 2 of 2 cubed plus, because the two things multiplied, I'm going to add their exponents. The logarithms are exponents. So log base 2 of 3 squared. And here you've got the deal where log base 2 of 2 goes away, it's just 3. And over here, since you've got, you can't really reduce the logarithm, but this 2 can be moved out. So anytime you are expanding, the directions say to expand. Anytime you have an exponent inside of here, make sure you pull it out front. You'll find in calculus that'll make things a lot easier. So I want to train you now to be looking to do that. And that's as far as we can take this thing by hand. But where you'll eventually get to is you might have something like this that's, for whatever reason, you got enough information to get that figured out, or maybe it's a real simple thing to do with calculus, whereas the original was maybe a lot more complicated. And I'm talking like 2 sheets of paper versus a couple lines. It's a big time saver, I promise. It'll save you a whole lot of time next year. On this one, let's expand one that's got a natural logarithm going on. So first up, go ahead and say natural log. And I'm going, instead of doing a radical, I'm going to do a rational exponent. And that's just kind of looking ahead, because I'm probably going to end up pulling the exponent out at some point. So that's natural log, or if it helps, you can always rewrite this as log log with a base of e. Some people really like to do that. You really want to get used to saying ln, but that's okay for now if you're still getting used to this. So an exponent can be pulled out front. I'm going to go ahead and do that. 1/2 times log a squared over b cubed. And you could have probably distributed the exponent right away. That's fine too if you want to do that. It's all going to wash out in the end anyway. So however you want to go about it. So 1/2 still up front. Now I'm going to add brackets because I'm expected to have 2 different logarithms happen here. It's a quotient rule, so log base e, I should be putting that e in there. Log base e of a squared minus log base e of b cubed. Okay. So now we got some exponents that can be pulled out. So this 2 can come out front. And I'm going to go ahead and start putting ln at this point. It's natural log base e. I think at this point, I think everything that might have confused you should be taken care of. So I'm going to go back. Log base e is natural log. So instead of having log e, I'm putting ln. It's just easier too to write. This 3 can come out. And again, ln of b. And we're almost done. Always look to see if there's more that can happen. 1/2 times 2 is just 1. So that'd be log a. So we definitely want to take that step. That'll make things a lot easier. And then here, it's, I would go ahead, since you've already canceled this out, I would distribute, make that 3/2 log b. So that is, in terms of calculus, and by next year you will definitely agree with me, because that is something you could be able to do in your head. This is going to involve a lot of complicated rules. So by next year, I think you'll agree with me that that's way easier. Finally, it's condensing. So we're taking the expanded form and going back to the logarithm. So probably not going to be used as much as expanding in calculus, but it's probably mostly just to kind of reinforce the process, make sure you can do it forwards and backwards. So keep that in mind. If you can do it backwards and forwards, you've really understood it, you've got it. So a lot of things going on here. One thing I guess I would look at right away, these are both log base a, so they should be able to be combined somehow. Logs are exponents. The logarithms are being added. When exponents were added, the big numbers were multiplied. So it's going to be a part where we can multiply the x and the x minus 4. And I'm going to go ahead and keep the 1/2 out here. Just follow order of operations. We always work in parentheses first, so this was all inside the parentheses. Those parentheses didn't have any work to be done, so I just ignored that. So it's log base a of x times x minus 4. Probably going to be easier to go ahead and distribute that out. You can always leave it as 2 separate factors if you realize it's going to be easier that way. Generally, it's easier to go ahead and distribute. All right, now we got 1/2 out front, which means that could be made an exponent. So log base a of the x squared minus 4x, and then the 1/2 can be made an exponent of that. And really at that point, there's not much more to do. I'm good with that. if it makes you feel better, if you're one of those people that really likes radicals, I'll go ahead and say, or you could do this. Some people really like to leave it this way, and if you do, it's fine. 1/2 power is a square root. So that would be x squared minus 4x under the radical.